In this problem, we're given a car moving with a known initial velocity of 28.5 meters per second, and it's coming up on a second car that's stationary, and that's 225 meters away. And then the main point of the problem is to find the minimum value of the acceleration that will get this car to stop before it collides with the stopped car in front of it. Note that the way I asked the question was for the magnitude of the minimum acceleration required to prevent a collision. So we know that acceleration is going to point to the left if our velocity is to the right. That guarantees the car will be slowing down. So if we use the traditional coordinate system where rightward is positive, well, this means our acceleration is negative. And what I did in the question is really just say, I want to know how big it is. You don't have to put the minus sign on there. And so the key point in this problem physically is that if we take the minimum magnitude of acceleration, our car is barely going to come to a stop right when it arrives at that parked car on the right. In other words, we know our final velocity v is going to be 0 when our position x is 225 meters. To finish listing our kinematic variables here, we're going to say the initial position was 0, so we're just implicitly putting our origin there, and we know the initial velocity. That was 28.5 meters per second. And what we're trying to get out of this is the acceleration. And our third kinematics equation, the one that's time independent, can do this for us in one step. Remember, that's v squared equals v naught squared plus 2a times the displacement x minus x naught. So our final velocity, we're going to plug in 0 for that. Our initial position, also 0. And if we put our numbers into the problem now, I have 0 equals v naught squared. That's 28.5 squared plus 2 times the acceleration times our final position, 225. And so we square that 28.5, we subtract it from both sides, and then divide by the numbers that are stuck to a, so that's 2 times 225. When all this is done, we arrive at an answer of negative 1.805 meters per second squared. So that's really the answer for the vector acceleration in the problem. It includes that minus sign as a leftward direction, but we were asked for the magnitude of this. So we're going to write a, meaning this time the magnitude of a is about 1.81 meters per second squared, where I just rounded to our traditional 3 significant digits. So in the follow-up question, we want to find out how long it takes to come to a stop at this minimum acceleration. And this one is really quick. We can get at it with our second kinematics equation that just expresses how our velocity changes with time. So v equals v naught plus at. We know the acceleration. We know the initial velocity, we know the final velocity. So we're going to get the time for the slowdown process out of this really quickly. Our final velocity is 0, the initial was 28.5. Our acceleration, again, we need to put the direction into this, is going to be negative 1.805, just keeping the extra precision there. And there's our unknown t. And if we round to 3 significant digits, we get an answer of about 15.8 seconds. And we're done. If you enjoyed this video, or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.